All right, welcome to The Explainer, where we break down big ideas right from the source. Today, we're diving into something really cool, a new paper that might just be the missing link between the AI we have now and, well, our own brains.
So let's kick things off with a really big question, one that kind of haunts the whole field of AI. We have these incredibly powerful systems, like the transformers behind models like GPT, but why are they so fundamentally different from how we think? This isn't just some philosophical puzzle. It's a practical problem that drives a massive amount of research today.
And this table really lays it all out, right? On one side, you've got modern AI. Think of it as this massive, powerful engine running on dense math. The problem? It's a total black box. We get an answer, but we don't always know how it got there. Then you look at the human brain. It's this incredibly elegant, efficient network that's amazing at generalizing its reasoning. Two totally different worlds. And look, this black box thing isn't just some academic debate. It has real-world consequences. It can lead to what's called failed reasoning. You've probably heard of the classic paperclip factory problem, right? It's a thought experiment where an AI is told to just make paperclips. It gets so good at it, so single-minded, that it eventually decides the best way to make more paperclips is to turn everything, the earth, us, you name it, into paperclips. It's a wild example for sure, but it gets to the heart of a huge risk. An AI that can't generalize its goals in a common-sense way is, well, it's unpredictable. Okay, so how do we bridge that gap? How do we build an AI that's not just smart, but also something we can actually understand and trust? Well, this is where the paper we're looking at today drops something new on the table, a potential breakthrough. And here it is. They're calling it the Dragon Hatchling, or BDH for short. So what is it? It's a whole new kind of large language model. The key phrase here is biologically inspired network. Instead of those dense, rigid structures we talked about, this thing is built from the ground up to act more like a brain, using these little, locally interacting neuron particles. All right, so it's built to look like a brain, but does it learn like a brain? That's the million-dollar question, right? And the answer is, pretty much yeah. It pulls together two really powerful ideas, one from pure logic and one straight out of neuroscience. So here's how it works. First, it has this fundamental rule of logic baked right in. It's called Modus Ponens. Super simple. If P is true and P leads to Q, then Q must be true. It's a basic building block for reasoning. But the second part, that's where things get really interesting. It uses something called Hebbian learning, which is a cornerstone of how we think our own brains work, how our brain cells actually form connections. And this quote right here, neurons that fire together, wire together. That says it all. It's the core idea behind Hebbian learning. If two of those little neuron particles in the Dragon Hatchling are active at the same time, the connection between them gets stronger. And that's it. That's how it learns to connect ideas and build this whole web of knowledge, basically mimicking how our own synapses work. Okay, so we've got this new model. It's inspired by the brain. It learns like the brain, but here's the real test. Does it actually work? I mean, can it compete with the big guys? The models we already know are incredibly powerful. Let's check out the results.
And wow, the results are pretty amazing. You're looking at a chart comparing its performance on standard language tasks against GPT-2, a really well-known transformer model. And look at that. They're basically neck and neck. This is huge. It proves you don't have to choose between performance and a model that's more understandable. You can have both.
This table, this is probably my favorite slide because it just lays it all out so perfectly. It positions the Dragon Hatchling right between the old-school transformers and actual brain models. And just look at that last row. Interpretability. For transformer, low. It's a black box. But for BDH, high, just like the brain. It's literally the bridge, using a structure that's sparse and modular, which is way, way more transparent than the inner workings of a typical transformer. So what does that high interpretability actually mean? It means we can peek under the hood. We can literally watch it think. The researchers could see that when the model was reasoning about a specific concept, the individual synapses connected to that idea would actually get stronger. We're going from that black box I keep mentioning to a glass box where we can see the gears of reasoning turning. You know, this is way bigger than just a clever bit of AI engineering. A breakthrough like this could have some really profound ripple effects, not just for AI, but for how we even understand intelligence itself. So why does this all matter? Well, for a few big reasons. For the people actually building AI, this opens up a whole new avenue for creating models that are powerful, efficient, and understandable. For brain scientists, this is amazing. It's a working model that can use to test theories about how our own minds create language and thought. And for society, for all of us, it's a big step toward what the paper calls axiomatic AI. Basically, AI that's built on rules we can understand, which makes it more foreseeable and, frankly, more reliable.
And this brings us right back to the paperclip problem, doesn't it? The whole point here is to build AI that we can trust to reason correctly, especially over long periods of time or on problems that are way more complex than anything it's seen before. Because this Dragon Hatchling model is scale-free, its behavior should be much more consistent and predictable, whether it's small model or a giant one.
And the authors leave us on this perfect, thought-provoking note. They didn't call it the dragon. They called it the Dragon Hatchling. This is just the very beginning. It's the proof of concept. So it leaves you with this massive question. If this is what the hatchling can do, what's going to happen when the dragon finally grows up? And that question, well, that could shape the entire future of AI.